All right, so before we begin today's class, just a quick little announcement for an upcoming event. So IUSB Psychology Club, in association with my research lab, is having this event on this Thursday, Comic Books and Psychology. So it's going to be a nice overview of the kind of research that I do and how comic book research is being used now to investigate how our minds work, how our communications work, and basically what are we able to process in this newly expanding visual world. So it's going to be Thursday, September 27th at 5:30 p.m. It's going to be in the cafeteria next to the grill. There will be free food and drinks. So if you want to stop on by, you can come. And if you can RSVP the Psych Club beforehand, either through Titan Atlas Facebook or the sbpsych@iusb.edu email, let them know that you're coming, but you don't have to. Feel free to drop on by to kind of see what this new developing area of research is all about. All right, so that is Thursday, September 27th at 5:30 in the cafeteria next to the grill. All right, so today what we're going to be doing is we are going to continue our look at probability and how it fits into this inferential statistics. So we introduced this idea last time when we took a look at the hypothetical situation, but not too hypothetical situation. What would happen if you were trying a new treatment with a sample of, for this example, 14 autistic students? So say that you were an educational psychologist, you had a classroom for students with autism, and you had these 14 students right here, and you develop a new treatment, a new way of educating these students using interactive technology to keep them engaged, to keep their attention focused. And let's say that you measure their learning outcomes, and their learning outcomes are better than if you didn't use the treatment. This is a wonderful result. This is something that you would hopefully want to use to help other individuals with autism. But without inferential statistics, you can't make that generalization. You can't go from the sample to the population. So there's no way to help any other student, any other child who has autism that is not in your class. You have no idea if this procedure is going to work for those students. So what we're working towards now, and we're almost there, is the use of inferential statistics, and that's what allows us to say something about a population of individuals, to generalize to the entire population of autistic children based only on a sample of 14, in this case, autistic children that we measured. So again, we know it works for these 14 students, and with inferential statistics, we can really make psychology powerful by being able to intelligently generalize to the population of autistic students all over the world. So what we're going to do today is we're going to introduce the idea of the normal curve. We foreshadowed this last time. The normal curve is a frequency distribution that occurs in nature and our universe over and over and over and over and over and over again. And then we'll talk about probability in the normal curve and how we use z-scores to address and use the normal curve table, how we read the table, and how you answer questions using that table. All right, so the normal curve. The normal curve, also known as the bell curve, it's a mathematical distribution. It's a theoretical distribution that occurs very often in nature. So it's that bell curve distribution that is pictured here. And this distribution, where you have the majority of individuals or the majority of scores come from the center of the distribution, and the frequency of scores decrease as the scores get more extreme. This is a distribution that occurs over and over and over again in our universe, and specifically in psychology occurs over and over and over and over again because of the nature of how people's behavior is determined. So this normal curve happens when a single factor, a single score, a single measure happens to be the outcome of many, many random factors that combine or cause this single score. So we have an animated demonstration of that right here. So this is a device that produces a normal curve. So basically it has a whole bunch of steel balls in one part of, or one side of this device. And what happens is you flip that device over and all these steel balls start pouring out. And at each level, there's what, like 10 levels. At each level, they're going to hit one of these pegs, and they have a chance to go left, and they have a chance to go right. And these random occurrences combine over and over and over again to form this distribution, because most balls are going to go left sometimes, they're going to go right sometimes, and they're the ones that are going to end up in the middle. Some of the balls, very few, are going to hit that peg and they're going to go left. And then they hit the next peg and they go left. And then they hit the next peg and they go left. And then they hit the next peg and they go left. And you get 10 lefts in a row. Those are the ones that are going to end up on the far left, right? So these balls here, they're the ones that happen to get 9 or 10 lefts in a row. The balls on this side, they're the ones that happen to get 9 or 10 rights in a row. And the ones in the middle, they're the ones that kind of get 5 right, 5 left, 6 right, 4 left. Those kind of combinations, which are much more common. So this is something that happens to humans over and over and over again, because our behaviors, our characteristics are oftentimes the culmination of many, many different random factors. So to give you one example, if you take a look at the height of adult women and adult men this is in the US, you can see that it is pretty much a normal curve. You have the small frequency of individuals in the extremes, either extremely short or extremely tall. You got most of the people in the middle. You have men on average being taller than women. But for each individual gender, we have women here, we have men here, it's approximately a normal curve, because many, many different things go into determining how tall an individual is. So there's first off things like genetics. Are your parents tall? Are both of them tall? Or is only one of them tall? Or are both of them short? There's things like diet. Have you eaten a healthy diet your entire life? There's things like being free from injury. Have you avoided major injuries your entire life? There's things like proper nutrition. Were you malnourished, at any point during your life? There's things like exercise. Have you been active your entire life? All of these things combine together, various random factors combine together, so that most people are somewhere in the middle. So if you look at men over here, most people are somewhere in that middle proportion, because they had good genetics, but they didn't have a good diet. They had a lot of exercise, but they got injured when they were young. There's sort of that combination of factors going one way or the other. The ones that are really tall over here, they're the ones that had everything line up correctly. So they had good genetics, they had a good diet, they avoided injury, they had lots of exercise, they weren't malnourished. All of those things end up contributing and combining to get that extreme score over there. So again, because in human behavior, especially in human characteristics, so many things combine together to form a single human characteristic. Many human characteristics happen to lie on this type of a normal curve, on this type of a bell curve. So another one that I found, which is even closer to a bell curve, were the SAT scores back in 2010. So SAT scores have to do with, a lot of things need to come together for very high SAT scores. So there's things like IQ is involved. Do you genetically have, a predisposition to higher intelligence? Did you get proper schooling? Excuse me. Did you get proper schooling? Did you have tutoring? Did you have a good rest the night before? Did you do one of the SAT prep courses? Do you suffer from test anxiety, right? And all of these things combine to form these SAT scores. And the people that are over here, they're the ones that studied, they're the ones with high intelligence, they're the ones that got tutors, they're the ones who had an excellent education, they're the ones who got a good night's sleep, they're the ones that don't have any sort of test anxiety, they're the ones that did amazing on the SATs. Everybody else over here would have a combination of some of those. So maybe they studied, but they didn't get a tutor. Maybe they had a great night's rest, but they have a little bit of test anxiety. And then all the way over here, these are the ones that have everything working against them. And again, it's rare to have either everything working against you or everything working for you, which is why the frequency of individuals in the tails of this distribution are lower, and the frequency of people in the center of the distribution are higher. And this is something that is a good tool to analyze different aspects of our world. So for example, and it's one thing to keep in mind that it's many random factors come together to form this distribution, these normal distributions. And this is important when you see data that has to deal with differences between races or different cultures. So for example, this is a report, this was in, when did this come out? 14 to 22 in 1979. Oh, I can't see the date on this, but this shows the frequency distributions for black and white individuals and what their IQ distributions are. And you can see that the distribution for black individuals is lower than the distribution for white individuals. So this is something that, again, people, if they forget, it's very important to remember that a normal distribution occurs when lots of random factors work together. Depending upon your political orientation, some people like to take a look at this and say, well, if you're racist, well, that's clearly genetic, right? It's got to be genetic. That's what this distribution says. If you're more into, I don't know what the other bent would be, but you would take a look at things like privilege and opportunity. You would take a look at things like the fact that IQ tests are often biased towards a particular culture. You would take a look at other random factors. So it's important to remember that for these frequency distributions, it's not one factor. If you ever see a normal distribution, remember, it's never one factor that causes that normal distribution. It's always a combination of factors that contribute. All right, so with the normal curve and probability. We talked about probability last time. We talked about proportions. We're going to talk about it specifically now with the normal curve because that's a curve, again, that comes up over and over and over in psychology and over and over in statistics. So we're going to take a look at how we can answer questions where if we have a normal curve that's a z-score normal curve, so we got a mean of 0 right here, we got a standard deviation of 1. If we have a normal curve that's a z-score normal curve, we can answer questions such as what percentage of the population scored below a score of 1.25. So we can figure out if that is 1.25 right there, what proportion of the population, what percent of the population is in that blue area. We're going to see today how to figure that out using the normal curve. We can also ask ourselves what score is bound in the middle 50% of the population. Let's say that you have a program that will only benefit people in the middle 50%. So it's not designed for people that are doing exceptionally well. Let's say it's an educational initiative. So you're looking at students with GPAs in the middle. It's not going to be good for GPAs that are extremely high. They don't need the help. It's not going to be good for GPAs that are extremely low. This program isn't designed for them. It's for GPAs in the middle 50%. What is the middle 50%? We're going to figure out how to discover that that is the middle 50%. Students that score above a z-score of minus 0.7 up to a z-score of 0.7. So all these sort of questions, something that might be on your radar coming up in the next few years. If you want to get into a grad school program and they say that we only accept applications from people that score in the top 10% of GREs, you might ask yourself, what score do I need to be in the top 10% of GREs? So if GREs are distributed normally, what score do you need? What z-score do you need to be in that top 10%, to be in that blue area right there? And as we're going to see, we can figure out that it's a z-score of 1.25. So how do we do this? Well, we do this by using z-scores and the normal curve table. So thankfully for us, because this distribution happened over and over and over and over again, mathematicians have analyzed it. They know the formula for it. If you ever look up the formula for a normal distribution, it is a monstrous formula. It's, just grad school mathematics in order to understand it. But thankfully, because it's happened over and over and over again, mathematicians with more skills than what we got have taken a look at it, and they've broken down everything we need to know and put it into a table that you can find in just about every single statistics textbook. So this is what we're going to do, and this is what we're going to use to answer any probability questions that we're going to ask with this normal curve, with a normal curve using z-scores and a normal curve table. So you'll notice that in your textbook, this is table A1. So it's the first table in the appendix. It should give you an idea of how important it is and how often you're going to use it. It's the first table, it's table A1. And what it does is it has 3 columns. One that lists the z-score. The second one lists the percent of the distribution between the mean and that z-score. And the third one lists the percent of the distribution from that z-score to infinity, i.e. the percent in the tail. So let's say that we wanted to know what is the percent in the tail when you have a z-score of 0.3. So if you have a z-score of 0.3, forget a z-score right there, of 0.3, what percentage of individuals are at that score or above that score? Basically, what percentage of individuals are in that blue area right there? So what we would do in that case is the first thing you want to do, and this is going to be true every single time, and this is something that I highly recommend because it's going to save you a lot of headaches. Whenever you're asked a question like what is the percent above z-score of 0.3, that's what we're asking right here. First thing I want you to do is draw a normal curve and draw in the area that you're interested in. So I did that on this. I did have an Excel sheet that'll do that. But basically all you want to do is take a piece of paper, draw a horrible normal distribution. Doesn't have to be accurate. This is 0 because it's a unit normal distribution table. It's z-scores, so the mean is 0. So 0.3, maybe it's right there. That's the area you're interested in. So it'll take you 5 seconds to do this, but it's going to save you a lot of headache when you're doing these questions. So we want to know what is the area in the top section, what is the area above a z-score of 0.3. So the first thing you do is you find that z-score of 0.3 in the z-score column. So you go to the table and you scan the column for the z-score associated with 0.3. Sorry, you scan the column for the z-score of 0.3. Then what you do is you have 2 columns here. One is the percent from the mean to the z-score. The other one is the percent in the tail. And you're going to have to ask yourself, which one of those numbers do I want? And if you haven't drawn your picture, you're going to have to go back to the question, reread it, try to figure it out one more time, and you have tons of problems and tons of possibilities to make an error. But if you drew it, you just take a look at your picture, or that one up there, and you say, which one does this look like? Does that look like this? Not really. Does this one look like this? That's the one. So you choose that column, and we find out that for a z-score of 0.3, 38.21% of the distribution is in that blue area, is above that z-score of 0.3. So far, so good? All right. Say we wanted to know instead how many people are below that z-score but above the mean, right? So how many people are below a z-score of 0.3, but are still above the mean. So again, we draw our distribution. We have that z-score. It doesn't have to be accurate. That's the z-score of 0.3. That's the mean. This is everybody that's below that z-score of 0.3, but is above the mean. That's what it looks like drawn to scale. So once again, we find that z-score of 0.3. And once again, we look at our columns. Is it this column or is it this column? We take a look at our picture. We ask which one does it look like. Looks like this first column over here. So we say, all right, in that case, we got a z-score of 0.3. And in between the mean and that z-score, we got 11.79% of the distribution. All right, so those are the two straightforward ones. Those are the ones that are actually in your unit normal distribution tables. The last one that is very common is when you're asked for a z-score and it's more than 50% of the distribution. So for example, if you want to know not what percentage of the population is above a z-score of 0.3, but what percentage of the population is below a z-score of 0.3. So we want to know what is that area right there. How many people are in that particular area? So we want to know what is the proportion of that blue area right there. And what you need to do for this, there's a number of different ways you can figure this out. One way that I like to do it is I like to break it up into two pieces. So you have one piece, which is the lower portion right here. So from 0, i.e. the center of the distribution, to the lower portion, that is 50%. That's half of your distribution. Because 0 is the mean, it cuts this distribution in half. That's 50%. And then what we need to do is we need to find out what is this remaining section over here. And thankfully, we have that column right here. So we find that z-score of 0.3. We want to know what this little section is right here. We drew it so we don't get confused. That's that little portion right there, 11.79. So we got 11.79 for this little piece right there. To that, we're going to add 50%, which is this half over here. And we get our answer of 61.79%. So that is the basic way to answer those three questions. And again, this is the only one where you kind of have to say to yourself, all right, well, this is not in any of these columns. So I got to split it up into two, and I'll take from 0 to the z-score, and then add to that 50%, which is the other half of the distribution. All right, so this is basically the three kind of standard questions that you can be asked. So again, if you have a z-score of 1, what proportion of the population is above a z-score of 1? It's that little area right there. Make sure you draw your distribution. It'll take a lot of the mental gymnastics off your mind. Draw it out. It doesn't have to be accurate. It doesn't have to be to scale, but it will let you know once you find your z-score, which column do you need to look in. We need to look in that column right there. So the people above, or the proportion above a z-score of 1.0 is 15.87%. The proportion between the mean and a z-score of 1, that blue proportion right there. Once again, draw it out so you don't get confused. Find that z-score, and we find the mean to that z-score. That proportion is 34.1. And then finally, how many people score below a z-score of 1.0? Once again, this time we have to split it up into two portions. One part is the part between the mean and the z-score, which in this case is 34.14. The other portion is the other half of the distribution, so we add another 50%, and we get 84.12%. And then the only kind of tricky one here, and the only last thing that we need to address, number one, sometimes you'll have a z-score of 0. That one can get a little bit confusing because that's exactly where the mean is. So for a z-score of 0, what's the percentage, for example, below that z-score? Well, for a z-score of 0, it cuts the distribution in half. So there is 50% in the tail, and that's what that column is indicating. Between the mean and a z-score, there's nothing. So that's why this percentage is 0. And then above that z-score, it's also, once again, 50%. So there's really just that one little tricky area, again, a z-score of 0 between the between the mean and that z-score, there's nothing. So that's why we have that one little confusing section for that z-score of 0. The last thing I want to mention about the unit normal distribution table, this normal curve table, is that in order to save space, because these tables, again, were made back in the days of when people used to print books and actually have to use paper to make them. In order to save space, you'll notice that there are no negatives for the z-scores in this table. So they don't have negative values anywhere in this table. So what you need to do if you're ever confronted with a negative score, if they ever say something like, what is the proportion of scores below negative 0.5, right? If you ever asked a question like this, what you need to do is you need to draw this out and then just mirror flip it and say, well, it's symmetrical. So the proportion below negative 0.5 is going to be the same as the proportion above 0.5. And that is listed in your unit normal distribution table. So don't get thrown off if you see a negative z-score. Just draw it out, flip it, mirror flip it, and you can use the table to find the values, and it's going to be the same because it's symmetrical for that positive z-score. All right, any questions on just the general idea of the unit normal distribution table? Okay, so the two major things that you can use the unit normal distribution table for is to either find a percentage if you're given a raw score, or to find a raw score if you're given a percentage. So we're going to take a look at both of those situations and the steps that you need to answer those questions. So let's first off start with a raw score, and we end with a percent. So in questions on the normal distribution table, you're either going to start with a raw score and end with a percent, or you start with a percent and end with a raw score. Those are basically the only two types of questions that you can have. So let's say that you're starting with a raw score and you want a percent. What's your step number one? Step number one is you need to convert your raw score into a z-score. So you need to find information on the mean, you need to find information on the standard deviation, it'll be in the question, and you need to take your score minus the mean divided by the standard deviation. You need to convert it into a z-score. And the reason for this is because this unit normal distribution table is all z-scores. There's millions of different normal curves, normal distributions out there in the world, but all of them can be converted into z-scores. All of them can be analyzed with this table. So that's your first move. You got to convert these raw scores into z-scores. Move number two, and this is not in your textbook, but I put that in there, draw your normal curve. I am trying to bring the percentage of students who do everything correctly and then look in the wrong column down to 0, right? That's like my goal for this class, so that every student, I can see it too. I mean, I see them do everything right and then they look in the wrong column. Draw your normal curve and you will never look in the wrong column. You don't want to do everything right and then fumble it at the 1 yard line. So draw your normal curve, make a rough estimate. I'll show you how to do this. Look up the percentage associated with your z-score on that normal curve table. Check your answer against step 3, and then you get your final answer. So let's take a look at, let's work an example in this. So for SATs have a mean of 500, each little individual section has a mean of 500, standard deviation of 100. What percentile rank are you if you scored a 333? So percentile rank is how many people scored as well or worse than you. That's what a percentile rank is. So if you're in the 98th percentile rank, you're doing pretty good. If you're below 50, you're below average on your percentile rank. So we're starting with a raw score. We want a percentile. What percentile rank are you if you score at a 333 when the mean is 500 and standard deviation is 100? All right, first thing we do is we convert this raw score into a z-score. You need to do this, otherwise you cannot access that unit normal distribution table. So we use the formula for converting a raw score to a z-score. We have the score minus the mean divided by the standard deviation. We plug in our values, 333 minus 500, and that divided by 100. And we end up with a z-score of minus 1.67. So that's our z-score. That's step one. We have a z-score of minus 1.67. Let me just write that down. Don't forget it. Z-score of minus 1.67. All right. Next thing we do, draw your normal curve. So we want to draw this normal curve. We just got our z-score. We want to know how many individuals scored below us. That's what a percentile rank is. So we're going to draw this curve. That's the curve that we draw. This is what's going to tell us which area to look for. So we want the percent below this z-score. We're going to look for the column that corresponds to that area. So have that somewhere drawn out that you can access, that you can look at when you're looking at your unit normal distribution table. So I'm actually going to draw that out. Oh, it's already kind of drawn out right here. Let's get rid of these guys. All right, so we actually have that little section drawn out here. And again, it doesn't have to be very good. 1.67, there we go. It's not accurate, it's not to scale, but it'll let us know which column to look in. All right, number 3, make a rough estimate. So this is a technique that'll get you in the ballpark and it'll prevent you from making an egregious error when you're doing your calculations. So to make a rough estimate, you have your unit normal distribution, you have your z-score distribution here. You're looking for that z-score of minus 1.67. And in your textbook, you'll see this figure here. And this is a figure that, once you work with it a little bit, you'll memorize it. But this is a figure that shows the proportion of the curve between certain scores. So what this figure is saying here is that between a z-score of 0 and minus 1, that's 34%, approximately 34% of the distribution. Between a z-score of minus 1 and minus 2, that's approximately 14% of the distribution. And I don't know why they have that minus 3 there. You can completely ignore it, because from a z-score of minus 2 on all the way, that's 2% of the distribution. And you can see that it's the same thing on the other side. It's symmetrical. So for between 0 and positive 1, 34% of the distribution. Between positive 1 and positive 2, 14% of the distribution. Ignore the plus 3. Between 2 all the way to infinity, that's 2% of your distribution. So how can we use this to make a rough estimate? Well, we have a z-score of minus 1.67. That is somewhere, we don't need to know exactly where, but that is somewhere between minus 1 and minus 2, right? Somewhere between those two values. So the first thing is we locate, where is it on this estimate figure? Where is it on these, on this make a rough estimate figure right there? And then the next thing is we determine what's the low end of our estimate and what's the high end of our estimate. So for example, we know that that's where our z-score is. So it's going to have to be this section of the distribution. Well, that's 2% right there. That's a little bit more. So we know whatever answer we get, it's going to be bigger than that section right there, and it's going to be smaller than that section right there. So this section right here is 2%. So our answer has to be bigger than 2%. This section here, this entire section here is 14% plus 2%. So our answer has to be less than 14 plus 2 equals 16%. So just by taking a look at this rough estimate, we can determine that our score, whatever we find, whatever we look up, on that table has to be somewhere between 2 and 16%. So this is an estimate, to be sure. This won't get you by anywhere in the real world, but this is just a way to check, to make sure that you haven't made a catastrophic error. So we know that our answer should be between 2 to 16%. And again, we do that by locating where we are on this z-score estimate, and then figuring out what number we need to be above. So we're definitely bigger than 2%. And what number do we need to be below? We're definitely smaller than 14 plus 2, or 16%. All right, so we made our rough estimate. We got to be between 2 and 16%. Whatever answer we get, it's going to be between 2 and 16%. Next thing we do is we look up the percentage associated with the z-score on the normal curve table. So remember that we wanted minus 1.67. Our unit normal distribution table does not have minuses. So what we do is we just flip that, mirror flip it, and bad at drawing these today. We mirror flip it, and that's the area that we want. That's the area that we're trying to look up. So we go to the z-scores, and we start here, and remember what you're working with. We're working with z-scores now, so we got to scan that z-score column, and we find 1.67. And then again, this is where a lot of students make the error where they got two choices. And if you got to try to keep it in your head which one you're trying to look for, you can make that mistake. So this is where after you find your z-score, go back to your picture. Looks like this. Go back to your estimate between 2 and 16% and find that in your distribution. The estimate sometimes will not differentiate between the two columns. The picture always will. So this is what we want. This does not look like that. This does look like that. So that 4.75, that's our answer. We check it against our estimate. 4.75 is between 2 and 16%. So that's our final answer. In this case, if you get a score of 333 on a section of the SATs, you are in the 4.75th percentile, which means that 95% of the population scored higher than you, which means that you probably should take that SAT again. All right, so that's starting with a raw score and ending up with a percentage. Any questions on that? Make sense? All right. The other thing that you can do with the normal curve table is you start with a percentage and you end up with a raw score. So these kind of questions are when somebody says to you, oh, I'm trying to get into grad school, for example. I need to be in the top 10%. What do I need to get on my GREs? So in this case, you're starting with the percentage. I want to be in the top 10%. What's the raw score that I need? So when you're starting with percentage, first off, draw your normal distribution curve. Again, this isn't in the textbook. This is a lifesaver. Please get in the habit of doing this. 5 seconds and you're done. Number 2, go to that figure, make your rough estimate. Number 3, you look up the z-score associated with that percentage. So now you're starting with the percentage. You find a percentage. You look up the associated z-score on the normal curve table. Step 4, check your answer against step 2. And then step 5, you finish off the calculation by converting that z-score into a raw score. So back to the SATs. So for an individual section, the mean is 500. The standard deviation is 100. What score will get you in the top 1% of those SAT scores? So what do you need to get into that top 1%? Notice that in this case, we're starting with a percentage. So that's a very important thing to reiterate one more time. In these questions, the first thing you got to ask yourself is, what am I starting with? If I'm starting with a percentage, I'm going to do these 5 steps. If, on the other hand, they give me a raw score, I'm going to do the previous 5 steps. So first off, indicate what is the information that you're given. In this case, it's a percentage. First thing, draw your normal curve. Once again, doesn't have to be pretty, doesn't have to be accurate. There it is. We want to know what do you need to get into the top 1%, what do you need to get into that blue area in order to get into that blue area right there. And it doesn't even have to be accurate. So I'll reuse this one over here. And this area that I colored in, this is way more than 1%. Well, let's just say it's 1% for this purposes. What is this z-score right there? And again, this will jog your memory. It'll help you not make that error when you're working with that normal distribution table. Let's get rid of that z-score. All right. Step 2, make that, whoops, there we go, 1% above. That's what we want. We got 99% below. Step number 2, make that rough estimate. So once again, we have, in this case, 1% above. We go back to our graph here. Again, this is from the textbook. And in this case, we don't know what the z-score is, but we know that we're in the top 1%. This is the top 2%. So we're somewhere in that tail, right? If that's the top 2%, then the top 1% has to be somewhere in that tail right there, right? Because it can't be back down here, because then we'd only be in the top 16 to 2%. So somewhere in here is going to be that top 1%. So what we do then is we figure out, well, what is the score in this case that's below the z-score, that's the next area below, and we come up with a z-score of 2. So again, we ignore the 3. I don't even know why that 3 is there in your textbooks. But a z-score of 2 and above gives you 2% of the distribution. So for a 1% portion of the distribution, we need a score that's higher than a z-score of 2. That's our estimate. So we don't know what answer we're going to end up with, but the answer, the z-score that we find, better be above a z-score of 2. Because a z-score of 2 will get you in the top 2%. So you got to go even better to make it into that top 1%. All right, so that's our rough estimate. We're looking for a z-score that's greater than 2. We have our drawing, we have our rough estimate. It's time to look up that z-score that's associated with that percentage on the normal curve table. Excuse me. So this is when you take a look at your picture that you drew and you say to yourself, I'm going to totally ignore this column over here. I'm looking for percentages in this column. I'm looking for percentages in the tail because that's what this looks like. I want this one over here. Now, when you're looking up percentages in the tail, sometimes you won't find that exact percentage. This is one of those cases. So in this case, we want to get as close to that exact percentage as we can. So what we're looking for is 1%. 0.99 is closer to 1% than 1.02. So that's a number that we're going to use. We double check it against our estimate. So check your answer against step 2. 0.99 for the percent in the tail gives us a z-score of 2.3. So we need a z-score greater than 2. So that makes sense. That checks out. So that z-score of 2.33, that gets you into the top 1%. And again, we check our answer against our rough estimate, and we see that it makes sense. We got more confidence that we did this correctly. So now the last thing we need to do is we need to convert that z-score into a raw score. Because if your friend is asking you, what score do I need to get into the top 1%, they don't want to hear about a z-score. They want to know what that raw score will be. So we go back to our formula for getting raw scores from z-scores. A raw score equals the mean plus the standard deviation multiplied by the z-score. We have all that information. The mean is 500. Standard deviation is 100. Our z-score we just figured out is 2.33. We plug that all in. We get a raw score of 733. So if you want to get into the top 1% on your SATs for each section, you want to score a 733 or higher in order to get into that top 1%. All right, so any questions on that before we wrap up our lesson for today? Okay, so you're now ready to tackle homework assignment, Chapter 4, Part 1. That's going to be due September 26th by midnight, so get started on that. And again, draw your normal distribution curve. I want to get to the point where nobody is making that mistake of doing everything correct and then looking in the wrong column. So please get into that habit of drawing your normal distribution curve. It'll just unload all those mental gymnastics, onto the piece of paper, leaving your brain free to do that other thinking. And then also keep up to date with your MyStatLab study plan. I haven't had a chance to update your previous MyStatLab points yet, so I'm going to get to that as soon as I can. But do stay up to date on those. Keep completing those mastery points, making sure that you get 100% on your pretest if you didn't get 100% already. All right, so that is all that I wanted to cover for today. So we got about half an hour left. So if people want to call it an early day, feel free. If on the other hand, you want to start up on some of your homework, or if you have any other questions about stuff that you've seen, let me know, call me over, and we'll make sure that everybody is firm on probability and the unit normal distribution table. All right, other than that, I'm done what I wanted to cover for today.